Am I right?
Yes, sir. Yes, sir.
Ah, okay, okay. So this is automatic load frequency controllers, another representation from different textbook resource support, wherein we have the turbine and generator mechanism is shown here. Generator and turbine combination. Turbine is driving the generator. Turbine is being operated using the resource by the valves and governor mechanism. You can see the rectangle box here. And another is speed control mechanism. How that controlling of speed and other thing is done in this context is shown here. Then actual speed governor is shown to you here. So this dotted rectangle entire block shows speed governing system, turbine energy system connected to a generator system, and here we have speed changer for that. It means this is the line which we have seen in the earlier interaction. So a request, speed changer, governor, turbine, and area with different inertia or frequency deviation, what it could result. So this is represented in this way so that we can view it very specifically. Governing mechanism has internally sub 3 blocks to view, and turbine and generator were shown like this way. Generator will have its angle and frequency feedback to the energy control system, electrical system, where we have a view of generator, network, load, etc., from which the required power is the demand, which is given to this turbine generator control, and the speed from the generator or a turbine shaft is fed back over here. And to control its 0 to max set point, governor speed changer will respond to ACE, area control error. My interest to show you here is ACE actually. How is that speed changer? In one of the objective question I have asked, which control loop is responsible for setting up of speed set points? It is the secondary ALFC. It means ACE is a stimulus for that. So that I wanted to project you. Speed changer gets the command or stimulus from the automatic generation control unit, which is having computed power, exchange, frequency, all those information were transformed as an energy, I mean, we can say signal mixer. Once that signal mixer transform that data into a command which should change the set point. So this set point changer will change the set point of the governor. Governor accordingly follow it till it can operate from minimum to maximum set point of that. So this become the primary closed loop and outer become secondary closed loop. In context to this, this is very interesting. I would like to show you one animation. Let us see how this automatic generation controller mechanism functions. Please tell me if this screen is not visible. I am opening a software, Power World. Are you able to see this screen on your visibility? Power World screen?
Yes, sir.
Single? Yeah, very nice then. So just let me brief you. This is one of the free software. One of the batch is using this software for the project. So there are so many terminals. You can see here horizontal lines, bus 1, 2, 3, 4 labeled 1, 2, 3, 4, 5. 5 bus layout. Each transmission line is interconnected by power measurement. What is the transfer going on? There are generators. You can see when I simulate it, you will be able to find generator symbols, and arrows show here dropping down or shooting up at the bus. They are called loads. So my interest to show you here is AGC, automatic generation controller on. AGC on. AGC on here. So what is my interest over here? When automatic generation control of this connected power system is working, interconnected they themselves, when the load change occur, how is that automatic to the change in load, these generators start accelerating their generation, increasing their generation to make the P balance. I wanted to project you. If I turn off the AGC is off. How is that balance happen? Who will take share of that? To simulate it, only the first generator, which we call as a reference bus, will respond for that. That I want to project to you. Let us say first, very simple. I will just run this simulation. You will find the generators are rotating, a symbolic representation. generators are driving and they are injecting the power to the grid, to the bus, and there is a flow of power using greenish. The greenish line show the transmission line which are carrying the power are well within their MVA transfer capacity. There is a big circle over here, you can see 94%. It would indicate the power flowing on this line is 94% of its capacity. That's an MVA, you can see. Here is 82%. It means while meeting the P balance of the requirement, these generators and this transmission mechanism interconnected, delivering the power to the end user. There is a load here, there is a load here, there is a load here, and another load here. You can see that some MWMVAR is the load. Arrow shows load. To meet the requirement, these generators are generating the megawatt and injecting to the grids. You can see them. Now, if I see 202.2 a megawatt at generator 2, 165 megawatt at generator number 1, 200, where is that another generator here, 91 here, 131 megawatt, not 131 here, 91.1 megawatt from another generator. It means I'm able to see what is the megawatt being injected by each generator for the current load P balance. Suppose AGC is on, this is a scenario. Now what I will trigger, AGC off, I will trigger. Let's watch how this increase of decrease of load. I will increase the load, some load point are here. How is that generator respond for that when there is an AGC on, when there is a AGC off, how balance is managed? Let us see, let AGC be on, all the generators have automatic generation controller on. What I will do, simply I will increase the generator. Can you see this one of the load here, 213 megawatt? I just use up arrow here. I will increase the arrow, increase the load megawatt more and more. You keep observing how is that generator megawatt 202 over here, 165 over here, and 91.1 megawatt over here. Keep changing according to my change of megawatt request, either this load or another load I can simulate to you. Let us watch it. Can you see? I'm incrementing the load. There is an increment of megawatt generation happening, 212, 176, 101, like this way. So whenever there is a load demand, I decrease the load. You can see there's a change in particular megawatt delivered. I increase this kind of this side load. Still I'll find. Can you see the change here? 217, 182, and 106. What is my context here is, whenever there is a balanced interconnected system in a locality, to have a P balance and Q balance, power system has to set up the commands to the requirement. So P balance, when it has to manage, the generator had to sync themselves automatically. For the change in demand, they must generate adequate megawatt, sharing the disturbance or load in proportion to their capacity and characteristics. That is one important characteristic that we find from power system operational control. So as the load changes, proportion to that change occurred in the system, generators identified to respond will respond in a proportion to there. You can see this. So suppose if this load, if I increase, for you to show how this generator's capacity will increase. Let's see here, I will increase the load here. Can you see there? There is an increment of megawatt is going. Hope all of you are able to observe megawatt 194 injection, 228 injection, 117.3 injection is happening. I increase the load here also. You can see there is a flow distribution of the flow on each line is happening. You can see this line is become highly burdened. 100% power flow is occurring on this line because this is an interconnected mode of operation between the bus to deliver the load. Definitely there will be an impact of this loading on the generator, so that these generators are striving themselves to manage the P balance. So this is what I wanted to show you. When AGC is on, automatically all the generator interconnected to the system start responding in proportion to the property, capacity, and characteristics as per the disturbance or load is considered. You may ask me, if the load decrement occur, naturally in the place of decrement, automatic decrement on each generation should take place till the capacity of their generation is considered. This is how one control, when I have AGC on, I can show you. Meantime, what I will do, I will reduce the load. Let us make the load safer. no load I will make or no line I will make it burden more, so that I can simulate another version of that. So I will reduce the generation. Let me bring the generation down. I think I have done sufficient generation down. Now we'll see all the edges are, let it be whatever the value, not to worry about right now. So all the generators are swinging hand in hand. AGC is on. Now what I will force? AGC off I will force. If the load increment occur, how is that these generator keep quiet? I would like to show you. So I will force this off. I will force this generator AGC off, and I will force this generator also off. You can see, I just, a message comes to me, I just ignore. Yes, off, off, and off. All the generators, automatic generation control, respond for the contingent change in load. Don't take care. Ignore is my condition. So if this is the case, if there occur load increment, automatically generators are not responding for the change in load, then who will respond for the change in demand? I would like to address. For that, you have to recall what is swing bus, what is reference bus, what is slack bus called as. It is assumed to be one of the biggest generator in the system, which is having enormous ability to deliver P and Q at certain specified voltage without any variation in their capacity. In that regard, in this context, when I make a load increase or decrease, contingent changes are responded by only the reference bus, because this is a software. This software has to simulate and show the responses or impacts of that. Hence, that is done by only the swing bus. Even though I turned it off, swing bus is the only bus by the software being compelled to respond and balance the load, so that the impact of change in load whenever AGC is off, how it is addressed. So let's see, I have turned it off, all the things. Let us increase the load here. Then observe the 176 megawatt of this generator, and another generator is how much? It is 64.9 megawatt, and this is 135. Only this generator will respond. Let us see what is going to happen. So I will just force. Can you see? Only Gen 1 is responding. This is 176 as it is, 64.9 as it is. I will increase the load here also. Can you see? Hope you are able to make a notice. 176.0 is turned off. It is not responding for the load change. And this is also not responding for the load change, wherever you increase the load in the system. So these two generators are not going to respond. Now you will find a tremendous pressure from this generator to the transmission line, injecting the power to the grid. There is a path for the delivery of power. You might ask me, why this line is getting burdened? Why not this? My friends, this is how the distribution of the power in the system takes place. It will be the shortest path for the delivery of load and low impedance path. So therefore, for the loads to be delivered at extreme right, extreme left, down, how is that interconnection? What is that best path available is chosen by it itself automatically. If you manually want to control, you have to isolate by circuit breaker. There you see red rectangle or square boxes, every line start and end of that. They are called circuit breakers. They are used to isolate or interconnect the line for our simulation. Now I have shown you when AGC is off, generators are not responding for the subsequent change in the load, is the only swing bus will respond for such delivery to show the system is still in the balance, till its capacity infinite. So therefore, this show you how the effect of automatic generation controller is really in practice of operation. So this simulation surely make you a knowledge that yes, there is a great study required for automatic generation control. Lot of mechanism, technology, economics is associated with this, because it is very important from the perspective of resource and balancing the load from the end user's perspective. So I have just tried to show you how AGC off will matter you the more, how AGC of a swing bus matter you to meet the requirement in this regard. So this is concerned to a single area. A single area, there are generator, and from that generating point, loads are being driven. This is how it is interconnected to you. Suppose the same scenario, If you imagine this concerned to a generating corporation A, say Karnataka, the neighbor state Tamil Nadu, Andhra Pradesh, like that. Imagine I have a energy corporations of state-wise interconnected by tie lines. I have asked one question. What do you mean by tie line? Tie line is an transmission infrastructure laid between corporations for trading of power to exchange, sell and borrow the power for the profit of their corporation and balance. So like that, imagine this kind of power system is interconnected to neighbor state power system at that time. How is that AGC of an area A, AGC of an another area B, another area C sync themselves? Then who will control this? For that I was speaking energy control center, central energy control center. We have to establish among these interconnected operations, so that that agency, that office will look for trading of power, exchange of power, billing of those parties who borrow, who sell for them appropriately. So if that is a scenario, I have another example to show you how this AGC function in interconnected operation of power system. For me, let me close this example. I will simulate that example also, so that it will become more insight for you to show you. So hope I'm opening another example which will give you a lot of insight for another interconnected mode of operation. Hope my slide is visible to you. Somebody please respond me. Somebody respond to me, please. This slide is visible to you. I'm moving the slide. Is it visible?
Yes.
Yeah, please. Now my interest. Yeah, please. It is just I'm zooming it. So this white surface area which the mouse I am hovering, this is one energy sector A. The pink shadow is another area B, and greenish or pista green, this is another area C. Imagine three areas, area 1, area 2, area 3 are interconnected for energy exchange. There are generator. In pink area, there is a generator, there is a load. In a greenish area, there is a generator, there is a load. Tie lines were laid between these two corporations. And in the white background area, we have generators, 1, 2, 3 like that. And we have so many transmission infrastructure laid in that area. And there is a tie line between 1 and 2 and 2 and 3 like that. It means there are tie lines exchanging power between the corporation and another corporation, and in between or within their corporation, they have their own load and meeting. If such a scenario is posed to you, you can see again in each generator AGC on, again have AGC on, AGC on, like that. There is a command given here. If interconnected operation of each area is considered, how automatic load frequency controlling concept AGC. So I'm using the word AGC. AGC shall mean ALFC AVR, because that is the role of automatic energy generation controller concept, to see to that voltage is balanced, and according to the change in load which the frequency get affected need to be addressed. Therefore, my presentation AGC shall not mean wrong. It is ALFC which I am trying to focus. So in such a scenario, if I simulate this software, it will show me the flow of power within this area and among the areas like this way. Let me show you. So when it is a balance situation, so there is a flow of power. You can just see between this white background area A and pinkish background area, this is the radiating tie line. Tie line is driving the power from white A areas to pink area. There is a flow of arrows here. You can see the arrow simulation. And between greenish area to whitish, there is a flow of power. And between pink and green, there is a flow of power by double circuit. This shows a small simulation effort. These generators in each area are trying to cope up to meet their area requirement. Now there is a big understanding from this concept is what is ACE? What is control area? I have asked you a question, and a conventional question I have asked, and two objectives also I have asked. What is ACE? ACE is an algebraic sum of the exchanged power from the corporation to the neighbor corporation minus the schedule exchange minus 10 times B, the frequency bias constant, and F actual minus F naught. You might have seen that ACE. What is that ACE error? Error is a stimulus for each area to function to balance A's to 0. In that due respect, automatic generation controller keep changing the set point of the generator till A's of that area become 0. You can see from the pink area perspective, it is a pumping power towards the green and borrowing power from white area. So it is keeping the balance. Net exchange from area 1, area 3, scheduled exchange and frequency bias of this has to be addressed by this area automatic generation controller. Similarly, in this the pista green area marked, you should see to that, and in the white area. And apart from this, you must see the cost effective operation, the cost of production, cost of exchange, and overall cost of operation system has to be seen very effectively. This example focuses very greatly on the concept of automatic generation controller and area control error to understand better. Now, what is my next step? When there is a AGC working, if I increase the load in one area, how is that second area start pumping more and more energy? I would like to focus. Let me make it magnified so that these two radiating lines you can visualize. Suppose if I increase the load at this point in the white area, how that delivery from green, from red get affected, you can just see. And AGCs are all on automatically. Generation at each area automatically modifies. You can see. I'm increasing the generation load at white surface area. Okay, you can see there is an overloading of this transmission section which is occur, and set point is going to have an influence. Now what I will do, I will change the load at this point. Okay, can you see? I'm increasing the load here. Okay, similarly, if I increase the load here, you can similarly see the similar effect here. Okay. Now, if I show you on other side, I just zoom this down, and if I increase the load here, you can see. The exchange of power is happening. Then if I make the AGC off, what will happen? Just see. AGC in one area, I'm turned off. Now I'm demanding power from neighbor area. Let us see how there will be a delivery of power takes place. You can see here, I'm increasing the load here. See, delivery from other area has to match this requirement when there is no automatic shift in set points. You can just, okay, it's giving a message to me. I just ignore the message and I just keep continuing. Just let me see higher capacity generation injection takes place or not. Till that point, we will try. There is an increasing injection going on. This line you can see the arrow dimension is increasing. That increasing dimension means higher power delivery. You can see this pi circle. Pi circle is filling up more and more, means delivery is increasing. Correct? Can you see? And this side, delivery from white area to pink area almost become diminished. There is no delivery. Everything is going on the right side here. You can just see. Correct? Now, if I increase the load here, you can just. One more thing you can notice here, the power flow was from white area, area A to pink second area. Now the arrows are reversed. Power flow occurring from pink shadow area to white shadow area. You can see this uprising arrows here in this line. This show you how that agreement upon the generating areas on the automatic generation controller concept keep working. Suppose if we want to see further increment over here, let me see by decrease the generation. I decrease the generation over here. You can see. I just start decreasing the generation here. Let generator generate less and less. You will find the effect of that. I just do. You can see the arrows are visible now. Arrows are going upward now. Hope you are able to see these arrows. Earlier, when I started automatic generation on, power was flowing from area 1 to area 2. Now it's going reverse. So again, this line you can see, they almost becoming partially red. So greenish and reddish. This means this is pumping more and more power from this area, from pista green C area, colored background. So this is how automatic generation in these areas are striving hard to balance the requirement of this area. Imagine this is agreed. These two corporations are agreed to fulfill the requirement of this area A, and the faults of this area are surely causing damage to this. Higher power of this area will cause the damage to a generator. This is the risk of agreement of interconnected operation. The corporations have to invest money on their switch gears such that switch gears are able to protect their infrastructure effectively in meeting this transaction for their safe and profit of corporation. This is how in meeting the requirement of some corporation, other corporations are put in risk. This is the role of energy control center operator. Electrical energy engineer's role is to see to it that this kind of risky environment, the unsafe mode of operation shall not be leaving or leave the system in danger. So the energy system dispatcher has to see to it that every hour of his execution of work shall not leave the system in insecure mode. We have seen what is securedness, what is reliability. So many points we have discussed, still we discuss in the next upcoming chapters. So the operation only for the point of profit of transaction should not be done. You should be ensure that securedness of the system must be there in meeting the requirement, so that else the disconnection of load or isolation from the defective things should be enforced. Now, if I trigger this AGC on, let's see how entire scenario is going to change. See now, again the reversal of arrow. Can you see here? Arrows got reversed. Power flow is occurring this way. This is the nature. We cannot find how the power flow occur on transmission line. Depending upon the interconnected system, there must be a flow forward, flow reverse on a transmission line, which was already installed carrying a forward. Immediately due to the change in structure or due to the fault at somewhere else, the impact of that will be somewhere else. This is how you must practice some softwares, at least to know how is that invisible concept of the power flow, indistinguishable nature of the power can be understood. Now I want to make you one good point to you. Indistinguishable nature of the power. This generator is injecting the power. This generator is injecting the power. Another generator injecting power. Power is clubbed and it is injected to the grid. Can I definitely distinguish in the flow of power in this line what is the value of power being pumped by this generator, this generator, this generator, like that? I cannot do. That is called indistinguishable, not indistinguishable nature. I cannot distinguish it. That is how in proportion to them I can share mathematically what is the contribution of this over this line, what is the contribution of this on this line. I can mathematically evaluate. That's how research is going on in this area. So therefore I would like to put a light on this. Such simulation software definitely enlighten us to think what is really happening in the operation and control of the power system. Meanwhile, the operation has to be so economic. I have this example posing you some cost of production from this left area, right area, top area. Something is put as an information box here. So that depends on that. The exchange must be operated by the energy control center. This is how before in putting the entire work on physical ground, such a simulation software, if modeled properly, can justify your mode of operation, whether it's going to be a profitable or going to be a loss. This is how engineering softwares help us to make visualization of the concepts. So hope these two examples made you little comfortable about what you mean by AGC, what you mean by such control. Let me force these AGC off. Let's see how power flow occur. You can see here, these two generators are striving again. This is not responding for the load change. Let me make a change in load here. Let us watch what is going to happen. Let me change. I'm increasing the power over here. And I will increase the power here also, load on this line also. Let's see how it happens. You can see this is stressfully loading the power. And these two lines, can you watch at the lower line? Earlier, they were pumping power to the right side. Now, what is happening? Pumping from right to left. This is the beauty of interconnected operation of power system. This is how people on accidentally die. Even though they don't know what is happening on the current line, what is the impact of other line if they are not able to ascertain. This is how accidents do happen. Can you imagine? The power flow occurring here is due to this load, and there is a generation setup going on for this demand over here, and that is pumping power to the grid invisibly. Where there is a demand, it is reaching, but these are striving to meet that demand. So this is how, this is very typical to visualize the vast interconnected energy system in a single view. This is a simple example of 5 to 6 bus make us to feel such a diversity of operation. If it is really an interconnected system of hundreds of bus to thousands of bus and tens thousands of transmission section, can you really imagine the difficulty and complexity of operation? It is not that easy by human beings. So therefore, these such softwares or such similar added real-time software can really make a sense out of that. Okay, so I tried my best to make you visualize what is the AGC, what is the impact of that using these two example. Hope I made this mechanism comfortable to you. Then later we have just seen how is that generator model from the swing bus m d square delta by dt square pm minus pe. This pm minus p is called accelerating power, is used to get into the generator model. The generator model, when there is a mechanical small, infinitesimally small request for a electrical need, infinitesimally small change in load, how is that area is going to respond? Area is going to turn out a change in frequency was seen from this swing equation. By having this swing equation suitably visualized, and to get the deviation in frequency or omega, how this integration taken on our right hand side, that is replaced over here using Laplace transform. Once we have Laplace transform, representation into block diagrams is very easier. Then later we took a load. The load model of an area depends on two parameters. This electrical load, whatever I have here, delta P, a small change in electric load. Suppose delta E, if I remove, it becomes PE. PE means electrical load. Electrical load comprising of two types of loads. One is frequency sensitive, frequency insensitive. If that is the scenario, this delta PE would definitely contain two parts. That's how it is written here. Delta PE can be delta PL, insensitive loads on frequency and sensitive loads of frequency. So here I have the delta PL, which is dependent on frequency, like inductive load, 2 pi FL, XL, inductive reactance change along with the frequency, and XC, capacitive compensations or capacitive kind of leading approach. So 1 by 2 pi FC, they are dependent on frequency. Invariably, I have from the loads perspective, electrical load, there can be insensitive to the frequency and sensitive to the frequency. That sensitiveness on the frequency is defined as D into delta omega or delta F. This D is called as load damping constant. This is also known as stiffness of the area. It is a response of change in load with respect to change in frequency. So how to understand this then? Suppose there is an area A locality. That locality has a generator and loads are connected. Suppose frequency of that area start falling down slowly to certain value. If the drop in frequency, what do you notice? There will be a change in frequency sensitive loads nature. That frequency sensitive load nature is represented by D. D is the change in demand with respect to change in frequency. D is called as delta PL to the delta omega or F. It is defined by this way. Change in frequency sensitive loads for a certain change in frequency is area's stiffness constant, load damping constant D into whatever is small change noticed. Say 50 hertz to 0.5 hertz, it has dipped. 0.5 into the value of D of that area. That makes the noticeable change in demand of that area due to frequency drop or frequency rise. Naturally, when frequency rise occur, naturally there will be XL will ride forward. In that due respect, sensitive to the frequency matters. In that regard, the electrical load, whatever we present to a generating area, delta P or P, need to be modeled suitably depending upon sensitivity of that to the frequency and insensitivity of that load to frequency. That is put as delta P, maybe infinitesimally small change in electrical demand is given as small change in electrical load which are insensitive to the frequency and sensitive to the frequency by having D of that area mentioned. So this is very interesting, because if the area is sensitive to the frequency, the operation of the energy control system of that area automatically going to change in a very different manner. If the area is not at all sensitive to the frequency, definitely its controls are different. That you can see numerically when we solve a problem, the area and a generator having a certain sensitivity to the load for the change in frequency and insensitive to the change in frequency. When I solve, you will find how governor find a change in their operation. Areas governor associated with the turbine for a area where there is no frequency sensitive loads. How is that change in frequency? If there is a sensitive loads are there, how is that change in frequency? This is experienced by the governors, because governors are the one going to correct for the change in frequency. So they will experience requirement of change in their set point. That we will see when we go to the numerical problems. For me, in this diagram, area and a mechanical infinitesimally small change request due to infinitesimally a very small change in load can cause a change in frequency in that area. And when the area load is considered, I can magnify the load as insensitive to the frequency and sensitive to the frequency. If this is the case, this one arrow which I have mentioned now become two part. One arrow due to delta PL insensitive, another arrow sensitive to the load with the frequency variation via the ratio D. Then this diagram needs a modification. This is what we have seen in the earlier interaction. So delta PM, the small mechanical supplement for any change to be addressed. For a change in demand, one is delta PL insensitive to the frequency, and the another is delta omega and D to the bed. So these two together represent delta PE. This is magnified as two parts. These two parts are put as blocks, feedback paths here. So one is delta omega S with the D sensitive to the frequency, one is insensitive to the frequency, and this summer block give that information to the area. Area's frequency response deviation is delta omega S. Now, when we have this block diagrams, control system block diagram represented, this feedback path is put in the forward block by transferring it to the forward block by weaving this way. What has been done? Delta PMFS as it is. This arrow is put upward just for the easiness. Then this feedback path, negatively fed feedback, is taken to the forward block by having 1 by 2HS plus D. This D is a delta omega and D is fed negatively in the feedback path. This feedback path is put in the forward block by transforming it to the, shifting it to the forward block. Like your control system, control shifting the summation block forward, shifting the summation block backward, making the two blocks parallel to the reduction, and making the feedback path to the forward function. This control system concept you might be remembering. This is put into the forward block function. You can see here, this become 1 by 2HS plus D has become. Now this become a generalized area and area response. Area is having a generator, H is called the area's response from the generator perspective, and D became frequency change. Generalized block diagram from the generator has come. B, even simplified into some other model in some of the books as we know, the 2H, this H and D can be replaced this way. The KPS is called as power system gain. Power system gain is called as 1 by D. So by replacing This D in this perspective, KPS is 1 by ratio 2H TPS, time constant of the power system, as 2H. By incorporating KPS and TPS in this block, I can revise this as a first order lag function KPS, which is a gain of the power system, 1 plus STPS, time constant of the system. So this is also one of the equivalent representation. So this is substituted H and D in terms of KP and TPS. So in solving the numerical problem, sometimes I may prefer KPS plus D or KPS by 1 plus STPS. Depending upon the data available in the problem, the area's response means the transfer function of the generator and load area is put either this way or this way. So this is called standard model of generator and load together. Load has its nature. So once we have this generator and load represented, it becomes necessary to view further if there is a droop characteristics, how this is going to share the load, etc. Now I have the same thing which is put as the area response and D back. This I will jump because I already have discussed. Now let us imagine such a generating area, such connected in parallel, responding for a change in load, how these will respond. So for that composite model, so this composite model will show you, this is called equivalent area, MS plus D. So M and again D are, M and H are again represented by this way. You can see here 2HS plus D, 2HS plus D, 1 by 2HS plus D. This 2H is replaced as M, MS plus D. M is again a inertia, M and H comparable, 2H equal to 1M, like that. So 1 by MS plus D is the area's complete generator and load model, and which has mechanical input infinitesimally small and electrical sensitive total loads here, because D has come to the forward block here. There is no need to mention delta omega back feedback here. It has already been taken in the forward block itself. Now such one generator, for any change in load, how this generator in an area is going to respond. For me, when a composite response is considered, I take you back. This is my requirement actually. When I have an equivalent area, several generator 1, 2, 3, 4, 5 for a certain load, how they will change their set points, how they share the load in proportion to their capacity and characteristics. I would like to, when do they change, how do they change, what is the change in frequency entire connected area experience for a change in load, I would like to present to you. Before understanding the composite response of a system, let us consider only one generator, a load and a area response by generator and a load. That's what I'm trying to do here. Only area's equivalent representation and only one generator and load. How is that change in load matter the area's generation, and how is that load change cause deviation in frequency? Then how this generator is going to cope up for the change in frequency and bring it back to steady. Then what is that nature? That's what I wanted to present you. Considering a single generator, a single load, and area generator and response is put as a transfer function. Now that one generator, when I consider PM1, load on that and area, it has a droop characteristics. The generator in that area or a generator which I am considering respond in this way, droop characteristics. As the load on that generator keep changing, the frequency falls. Then governor, if at all, that generator will command or is set to command, it will change the set point in proportion to the drop in the frequency. Then droop nature of the generator become an important thing to visualize. Now I have shown you a certain droop curve of a one generator. Let it be F and P plotted, a droop nature. Let there be a basic F naught base frequency. It was working initially. And it was delivering power P1. Suddenly, load is increasing. Delta PL nothing but increase in load demand. For this increase in load demand, definitely delta omega has fallen down, and delta PM additional mechanical power from the turbine has to come. So that what is this share? What is that really seen as a drop in frequency from single generator perspective? If you want to understand it, this is how we can see its curve plot of frequency versus power. It was steady at a certain F naught delivering P1 megawatt. Suddenly load increased. When the load is increased, the operating point in load, let's say P1 dash is the demand. For this P1 dash in the demand, sudden jump in power requirement is delta P1. We can see here delta P1 is the shift in demand from base P1 because steady state delivering equally and appropriately at F naught frequency. Suddenly demand made it to suffer. Generation has to cope up by delta P1 extra. If the frequency is observed, this droop nature definitely make, if there is no governor operation, definitely this meeting up of extra power delta P1 is there with the capacitor generator. It would have coincide on this line at this F, that become F dash. Definitely F naught and F, if I say F dash is less than F naught, it is experiencing a drop of frequency. That's called delta F. Delta F is change in frequency. For what? Delta P1. For a change in demand, delta F has noticed. So this ratio, if I write, that become droop of that particular generator. So droop is delta F by delta P. That is called R of that generator. In that proportion, generator is going to respond, or turbine governors are going to open the valve so that generator builds the power. So therefore, this is the scenario of single generator I am trying to convey. If I have a number of generator, such number of curves I will have. Definitely delta F is common to every generator connected in parallel. So this is easy to understand from single generator perspective. Then how it is being done? Let's see. This is delta PL. Whatever is the small change in power is demanded from the area, let it be delta PL, which is equal to delta PG, what right now the generation is going on, minus the demand, what is extra increased, whatever is that. So this is called contingent demand. So delta PL is what is going on, what is actually the demand. This difference is delta PL. Then we know that generator will respond in proportion to its characteristics, which is called delta PG. Share taken by the generator for the drop of frequency is delta F by R. It's a droop comes into picture. How much is the set point? How much is the incremental power changed by the generator for a drop in frequency to be addressed? That is delta F by R. We know if you take this R other side, delta F by delta PG is the droop of the generator. In that regard, delta F by R nothing but change in generation that the generator has to look forward to address this error to delta F to nullify. Therefore, with the help of governor droop characteristics, this generator respond to see to that delta F goes 0. And delta PD is now equal to D into delta F. So delta PD is what? The incremental change in the load is frequency sensitive load. This drop definitely makes D. What is D? Area's stiffness. D into delta F. Then I have this equation. Delta PL is equal to delta PG. Who is responding? Generator is responding. In what way? Delta F by R minus. In this regard, generator is going to respond for your demand. And this demand, what is nature, which is seen now is D delta F. From this equation, I will find this is the response from the generator. This is the area's reflection on the drop in frequency. Together is a change in load to be addressed. For this to be addressed, there is a term delta F. So delta F, you take it out. Delta F equal to minus 1 by R minus D. Take this minus outside again. It become delta F equal to minus delta PL divided by 1 by R plus D. Now we got a simple equation. Whenever there is a generator in a area, single generator meeting a load, and there is a load which is sensitive to the frequency as well as insensitive to the frequency, together there is a change in frequency due to the change in power demand. This is the equation going to help. What is that? Delta PL is nothing but net change in demand divided by 1 by R, droop nature of the generator governor going to respond, plus area stiffness. What is area stiffness? Change in load with respect to frequency. It's called composite load constant. If the area is sensitive to the frequency, D appear here. If area is not sensitive to the frequency, eliminate the D. What is this? Delta PL by 1 by R. R you can take the numerator. So this is how there is a drop in frequency noticed. So this is observed in the energy control center of a generator. According to the permitted delta F, it is permitted. If it is going bound above, automatically there must be a governing action to address this delta F to within the range, bring within the range. Therefore, this is from single generator perspective. I have one generator, only R of that, and delta PL of the particular area. Delta F is the change in frequency noticed, and D is areas D. Now, if I have multiple generator in a generating station supplying to the A area, can I have a D1, D2, D3? Definitely no. One area means D is unique to that area. R is R1 for generator 1, R2 for generator 2, like that. R is nothing but droop nature associated with the governor mechanisms. It depends on types. But area, when I say a geographical area, D is constant for that. So in that way, delta F, the change in frequency experienced by a certain area on a change of load, is measured by delta F equal to delta PL divided by 1 by R plus D. Later, we represent this denominator by a constant beta. This beta is called as area frequency bias. We'll see in the next slides for that. So let us say there is a one generator for a change in load. How is that deviation in the frequency? Either it's delta omega or delta F, depending upon the type of the book presentation, people refer it. We can refer delta omega, delta F. Only thing is radians. This is in hertz. So therefore, this delta F is given by change in load to the 1 by R plus D if the area is having sensitive loads in the notation. If sensitive loads are not there, D you make it 0. This is with respect to single. Now imagine if there are multiple generators, what would happen? In the place of R, I may have R1, 1 by R2, 1 by R3, like that. This 1 by R concept will expand. Then how is that? We can see that. We can see composite model. When a composite model is considered, definitely I have a number of generators here. Generator 1, generator 2, generator 3 connected in synchronism, delivering mechanical input to the turbines, and for a change in load request from the area, it has to address and balance. So therefore, this become composite model. For that again, for any change in load, we can see what is the generation, what is the demand here. Then I can write this change in load shared by each generator like earlier equation. Can you see here what I did here? This delta PL, which is equal to delta F by R, only one generator was there. Now it become delta F by R1 from generator 1, delta F by R2 from second generator, third, fourth. This term is going to have number of fractions depending upon number of generator, but the area sensitivity to the frequency remain unique to area. This expression is elaborated over here. Can you see here? Delta PL equal to delta PG minus delta PD. Delta PD is sensitive load, D into delta F. D is unique to any area. This area is having several generator, doesn't matter, it's the unique D for that area, D into delta F. But this share, how is that? Demand is shared by different generator, E is given by delta F by R1 proportion to the capacity by 1 minus delta F by R2, second generator, third, fourth, fifth, nth generator. If I have n generator in the concurrent occurrence here, all the generator respond according to their group nature. So delta PL is addressed as minus delta F by R1 minus delta F by R2 all together minus the area response for the change in frequency. So if I write this first term as an simplified way, you can see delta F divided by R equivalent, something I wrote here, delta F by R equivalent. So what is this R equivalent? Equivalent droop of generator in a plant. Now how do you get to know? Look at the diagrams I mentioned. Let us take two generator. Each generator, unit 1, unit 2 have their respective droops for a change in particular set point. Certain point they are working with the F0 frequency, P1, P2 where the deliveries like P1, P2, P3, P4 where the megawatt injected for the balance. Suddenly load increment is noticed. What is that change in generation? Say delta P1. In the second generator, delta P2. Like that you have n curves. So delta P1, delta P2, delta Pn are the incremental changes in generator. That's what I have here. Delta PG means what? Delta PG1, delta PG2, delta PGT. What is that really by value? Delta F by R1, delta F by R2 by second generator. Like that, each generator's supplement for the demand is put by their droop value as delta F by R1 from the curve of that first generator, from the curve of second, third, fourth, like this way. I have shown it nominally 2 here. Likewise, I have several generator. Now I will find R1, R2, R3 as a droop's nature. Equivalent droop of generator swinging in hand in a plant, I can write as R equivalent. You can see in the where I have here R equivalent is 1 divided by 1 by R1 droop of first machine, 1 by R2 plus the last machine. This representation is becoming equivalent droop of all the generator in a plant. If there are 2, R1, R2, like that. So that is represented as delta F by R equivalent with a negative minus D into delta F, which is again simplified as delta F is taken out, minus 1 by R equivalent minus D delta F. And this is called change in demand. And take this minus out and put other side. Therefore, what is delta F? The frequency deviation experienced by a composite model for a change in load. That is what I wanted to convey. In case of this earlier, what I did, change in frequency experienced by a single generator for a change in load. That was delta F equal to delta PL 1 by R, PL divided by 1 by R plus D. Same way, when I have a composite model, number of generators swinging hand in hand, experiencing a change in load, surely experience a change in frequency. Then what is that change in frequency? Delta F. Delta F equal to delta PL negative. This negative sign I transfer this side. Delta PL minus divided by 1 by R equivalent plus D. This become the area response. Now you can see 1 by R equivalent has come here. Earlier in the slide, single machine, it was only 1 by R. Now I hope you are very clear. When a single generator is considered, it is delta PL by 1 by R plus D. If the number of generators are considered as a composite model, delta PL minus divided by, in the place of 1 by R, it become 1 by R equivalent. 1 by R equivalent is by this way. What is R equivalent? Is 1 by R1 plus 1 by R2 plus 1 by Rn. So this is how the deviation in frequency experienced by a composite model can be concluded by simple through 2 or 3 steps. Now in this D is called composite load damping constant. Now I have several generator pumping energy and area is drawing the power and delivering to the load. Loads are sensitive to the frequency by D. For change in frequency, how is that change in load? That is put by D, dou PL by dou PF, or delta PL by delta F. Then the composite frequency response of the system is given by, I was speaking, the denominator of this frequency deviation term, denominator is called as area frequency response or bias. This is given by beta, delta PL by delta FSS. Therefore, this is called as 1 by R equivalent plus D. This term is called as B or beta. This is called area frequency response. So this is going to help you to solve a lot more numerical problems. The one which I have shown you, single area, delta F equal to delta PL minus divided by 1 by R plus D. In a single area, single generator, or we call it as an isolated area. Isolated area means single unit operating or a single plant this way. When I have plants with a several generator, this concept comes into picture. Definitely 1 by R equivalent rush into the denominator. This is how the composite model of a generator comes to our conclusion. So then I have simple numerical example to revisit your understanding. When is a composite model studied in basics? So in fact, this is studied as a single machine. When I have a single machine, the change in frequency experienced, drop in frequency noticed, if you want to calculate, you require delta F. Then what is delta F? Delta PL minus divided by 1 by R plus D. How to compute this? See this example. This example show you a 500 megawatt generator has a speed regulation 3%. Capacity of generator, droop nature is given. The frequency drops by 0.1 hertz due to increased load. Delta F is given. Drop in frequency is 0.1 hertz due to change in load. Find the increase in turbine power if reference power setting is not changed. Speed changer is not worked out. Only governor has to respond for the change in frequency. Nothing but what is that extra turbine power, delta PM, to be increased. What is that valve opening to supplement mechanical power is the question. What should be the change in reference power setting if turbine power is to remain unchanged? So you recall back, when the governor mechanism is going to operate, it has a minimum and maximum boundaries, and it's going to operate in that. If governor is stalled, not able to cope up, speed changer has to come from LHS side, means from the reference set point change. So from a reference point I can change, or from the turbine governor mechanism I can change the requirement here. Here it is asked to change reference point only, not the turbine. Then by having this content understood, how we can solve this? See, this is a very simple problem solution. This is worth 8 marks problem. This kind of problem, if they are posed in the exam, worth 8 marks from the basic type 1. So therefore, droop is given 3%. What is the droop by nature? If I go back, what is droop? Delta F by delta P. You can see delta F by delta P is droop. It's called 3%. 3% of what? The ratios. So 50 by 500. Why it is being done? See the units here. This is hertz per megawatt. This is actually 0.03 into 50. When I take this 100%, 3%, it becomes 0.03. 0.03 on the base frequency 50. 0.03 into 50. Okay, divided by the base of the particular generator, that become so many hertz deviation for every megawatt of change. It's called hertz per megawatt. But for you, what is the problem explanation? Drop notice is 0.1 hertz. Droop is 0.003 hertz is a change for every megawatt, or for every drop of 0.003 hertz, 1 megawatt is a change in the experience. That's called droop. So therefore, it should be seen from the governor's point of view. 0.003 hertz change, it will increase a megawatt like that. So therefore, for 0.1 hertz drop, what is that change experienced in set point? That is again same equation, delta P equal to delta F by R. So this delta P is the requirement. So delta F is given as a 0.1. 0.1 divided by 0.003 refers to 33.33 megawatt. See here, it is supposed to operate at certain frequency. Frequency is not given. Let it be 50 hertz. So it is taken as a 50 here. If 50 hertz is having 0.1 dip, it is 49.9 then. Therefore, 0.1 hertz is the drop. So 0.1 hertz divided by hertz per megawatt correction. If I apply, it is in need of 33.33 megawatt for this drop to be corrected. Change in reference point has to be 33.33 megawatt. So you see the text here. Increase in turbine power must be equal to 33.33 megawatt if reference power setting remain unchanged. See how it is. Reference power setting unchanged. If this increase has to be blocked, means then the reference setting should be changed such that P ref minus delta F by R equal to 0. So what is this exactly? I go back and show you where I am exactly. This is actually turbine governor characteristics. You can see here where we have seen this point, delta F. One of the equation we have seen. Yeah, this one. Delta P equal to delta F and this R. One more is there. I think this one only. Delta P reference equal to delta P reference minus delta F by R equal to 0 from the governor's operation. Means this we have seen in module number 2. 2B we have discussed this. I remember when I was speaking about the fly ball governor mechanism. You recall back, please. That's what there we have come across this point. Delta P reference minus the delta F by R equal to 0. So what is that reference point required as a shift? This to turn on RHS side, the same value repeats here. So this should leave the turbine power unchanged, only reference point to be changed by 33.33 megawatt. It means this drop in frequency means demanding increment change in power set point. This we have to set as a change in power to address this 0.1 hertz. This one simple example. Let us see one more example. A 250 megawatt generator has R regulating characteristics of 4% or 0.04 PU. What will be the change in turbine power? You can see this. What will be the change in turbine power expected as an increase in the bracket knowledge? Turbine power if the frequency drops by 0.15 hertz with no change in reference point. See here, reference point should not be changed. Turbine only need to accelerate by governor's action. That's considering the base frequency of 50, F not equal to 50 hertz. So with this again same workout. R is 4%. Meaning of 4%, I have revisited here. 4 change in frequency, change in. So what is 4% again? 4% on base frequency. You can see here 0.04 into 50, nothing but if there is a change of 2 hertz, what is the control you can do is 0 to. That's the meaning of droop. Droop characteristics of a generator means for a certain percent change of the frequency, give you a freedom of control of minimum to its max capacity control. Therefore, 2 hertz R equal to hertz per megawatt. The same thing is being done. R equal to 0.04 into 50, 0.04 into 50, 250. This became 0.08 hertz per megawatt. This governor is going to correct for every 0.08 hertz 1 megawatt shift is the meaning of this one. So if notice of 1 megawatt 0.08 frequency, this is how the droop nature of the system is experiencing. So as per the data, what is the drop in frequency given? 0.15 hertz. You can see delta F is 0.15 hertz. The change in turbine power expected is equal to, can you see this? Delta F divided by R. Delta F minus delta F minus of is also a drop. This is also a drop. Hence, inside the bracket, there is a minus. Minus 0.15 divided by 0.08. There is already a minus in the droop characteristics, which was seen here like this. You can see. This will compute the change in turbine power as 18 points. So this is a simple another example in a single generator area. So if there is a change in load where the frequency is dropped, how much that the generator governor need to do, or how much is the set point change if governor is not going to do, only set point has to do. This is the power increment we are finding. So here 18.7 the turbine acceleration incremental change in power is 18.75 to address 0.15 hertz drop back to nominal. This is the simple another example cites you to the application, which make you little magnified approach. A 500 megawatt generator has a regulating characteristics of 5%. So why I'm making more and more problem means these are the worth 8 marks problem. If you do not touch, -8 is sure for you. That's why we have to view as many as problems possible. At least you will do some part of the work where bits and pieces plus to that in partial steps, at least in your process of approach. In that due respect, I keep solving or presenting you more and more problems. So a 500 megawatt generator regulating characteristics of 5%. First question, what will change in turbine power? Nothing but increase if frequency drops by 0.1 hertz. It is like a previous problem, first part, with no change in reference point. Nothing but like this problem, this procedure. Second one, if the frequency, where is this? Here. What will be the change in reference point if turbine power must remain unaltered? Turbine will not keep changing. Only reference point should change. Take base frequency equal to 50. Second point is nothing but your first problem, this problem. So together, this problem and this problem are there in a single problem. This can be one of the best problem for your exam perspective. Case 1, case problem. This kind of scenarios would be a best scope for your exams. So let us take the first part. As per the data given, R equal to delta F by P, we know. Then delta F is 5%. 5% divided by its capacity, it becomes R is hertz per megawatt. You might ask in this chapter, when we were working, we haven't done, we took simply percentage. Hope many of you will be wondering here. Definitely, because I am working on AGC, ALFC, automatic load frequency controller concepts. I am working where there is a change in load, frequency get affected. To address the frequency, megawatt supplement I have to do. In that due respect, change in frequency and change in power is my need. Hence, groups are converted to hertz per megawatt. The same thing we have not done in model number basic introduction. We have done some simple of power by X megawatt by generator 1 and another megawatt 600 minus X by another generator. There we have not done this kind. Hope you must remember. Problems look very similar in model number 2, model number 3, like that. But the method of solving them keep changing a bit by value. Alerting now, keep monitoring carefully, perspective only. Change in frequency mentioned here is 0.1 hertz. Therefore, if delta F is 0.1 hertz, change in turbine is minus of that frequency drop divided by R. Like this only. The same thing I wrote here. Minus delta F by R. Minus delta F by R. When I mention this, 20, this drop of, if at all noticed, required to adjust it back to 0 means 20 megawatt from the generator, from the turbine increment is to accelerate the power by 20 megawatt so that this 0.1 hertz drop is corrected back to zero error. This is the first requirement. The second is reference point must be shifted and turbine power must be kept constant. Change in turbine should not change the power. Only the reference point should change. Then the change in set point, reference point, nothing but delta P ref. This should be delta P ref. Hence I wrote by point power, reference point increment power is equal to minus delta F by R, minus delta F by R. This turns minus 20. So you might ask me, why? This is what input to the generator side mechanically, which is coupled. This is the set point at the control loop block diagram. Control loop block diagram, the increase in set point, decrease in set point. This is negative, means the set point. So I can go, you might have seen that particular, I think I may not be having this here in this diagram. If I possible, I can show you. Here only you can see this. I have here this one. So in this I am speaking about, this is the set point changer. This changer will have this input here. Minus means increase, plus means decrease. Even if you see one more diagram, I think in this slide. So that is how this question focus you in that way. It means there is a need of, come back to this problem here. So this is minus 20 megawatt is a set point that increase even in the turbine governor mechanism, raise or lower the set point, something was there. So in that regard, this minus. So even if you do not mention this minus, 20 megawatt set point change is needed. That is enough. That's why I wrote here, lower the set point in the speed changer by 20 megawatt. Minus I have omitted off. This is to convince, so that y minus, y plus, textually I can text it and I can make the data corrected. This way also I can make my set points done. This is the one problem making you to think both the concepts. Turbine power incremental, reference not changing. Reference changing, turbine power unaltered. Both the situation. You can see this drop is because of a power demand. What is the demand? 20 megawatt. 20 megawatt. Who will correct matter you? In this first part, turbine is going to correct by governor role. Here, it is the set, so that 20 megawatt directly corrected at the generator side. This way, demand of 0.1 hertz arrest back to zero is 20 megawatt. That will not change.